When we're not certain how long tasks will take, PERT analysis allows us to gauge the risk associated with any given deadline. You can see that in this scenario. Scenario 3A appears to confirm the technical director's argument that there is no need to spend on crashing tasks, that is to say, getting them done in a hurry, within the project because the expected completion time without extra spending is 6.75 days, and the client needs the project finished in 7 days. Okay, interesting fact. Missing the 7-day deadline would be disastrous for the client. Oh, so you can see the question posed there. We're interested, fine. What would be the probability of actually being done in 6.75 days, 6 3/4 days? Because that certainly would be in time for the sensitive 7-day deadline. Now 6.75 days, if you remember from the scenario before, is the expected completion time of the project. So we would think that the probability of being done in 6.75 days would be fairly safe. Okay, now there is a way to calculate that probability exactly. One of the things that we have to remember is that the probability of completing the project in 6.75 days is the joint probability of completing each and every one of the paths in 6.75 days. It is the joint probability of completing all the paths in that time. All right, so all we need to do is to calculate the probability of finishing within 6.75 days. Wait a minute, we want to calculate the probability of completing each path through the project in 6.75 days. Then we can roll it up into a single answer. Okay, fine. How do we calculate the probability associated with the paths? First off, a path is any route from start to end. So if you go back to scenario 3A, where we had the actual network in front of us, you'll notice that there are 3 paths or 3 potential routes through the network. One of them is quite short. Let's just begin with that one. That path is A, E, I. That's a sequence of activities, A, E, and I. Now, we ask ourselves, what is the length of that path? Well, you add the expected time for A plus the expected time for task E plus the expected time for task I. I did that in my notes. Oh, that path is quite short. It is 2.75 days long when you add up these durations. Okay, now, in order to calculate the probability that we'll be done with just that sequence of 3 tasks in 6.5 days, we need to now identify the standard deviation in the path. What we have, the 2.75, is its mean, or its expected length. But what is the standard deviation in the path? You say, huh? Why? Why do we need to do that? Because remember, we believe that this path, what actually happens once we complete tasks A, E, and I, will follow a normal distribution of which that is the center, 2.75. But we're curious also, what is the standard deviation? How much wobble is there in reality? Okay. How do we find the standard deviation associated with a path? We have to remember that, wait a minute, the standard deviation is the square root of the variance. You say, well, yeah, okay. And the variance in a path is really easy to find. The variance in a path is the sum of the variances along that path. Oh, so here, find variance first, because variance is just the standard deviation squared. Well, how am I supposed to do that? Oh, right. Remember back from scenario 3A that we calculated variances because they were the pessimistic time minus the optimistic time divided by 6 squared. And we did that for each and every one of the tasks. And then we wound up back then not using that information, but we said, you know, we'll store that because we may be able to use it later. Now is the time to use that information. For instance, I'm checking my work and I remember that the variance in task A was 0.0069. That's what we got when we filled out that formula. Okay, and then the variance in task E was 0.0278, and then the variance in task I was 0.0278. All right, why am I lining these all up in a stack? Because I want to add them. I add them up, I get 0.0625, and you say, great, are we done here? Have we got the answer? We've got the variance in that path. I want the standard deviation, right? That's the variance. The standard deviation is the square root of that. The square root of that is 0.25, the square root of 0.0625. So this is, for this column, for that path, this is the standard deviation right here. Maybe I'll just sort of punch it with a bolder color of ink. Oh, all right. You say, wait, I thought we were calculating like some kind of risk of 6.75 days. We're almost there. Because now what we know is that the outcome of AEI follows a normal distribution. The center is 2.75. The standard deviation just found it. You know, I did a question mark here, but I could ink over that and say, well, you know, it's 0.25. And I'm asking a question about 6.75, which is somewhere out here. So I really wish I had a table that told me that if you drew a line, right, at 6.75, because that's the target, that's the question we're asking, the table would just tell me what the area of the curve is to the left of the 6.75. Why? Because we believe that's our vision of risk. The probability that AEI will take up to but no more than 6.75 days is the equivalent of how much of that normal curve is successfully cut off to the left of 6.75 days. Oh, well, I don't have a table that tells me the area that is underneath the curve to the left of 6.75 for a curve. The center happens to be 2.75 and its standard deviation happens to be 0.12 or 0.25. I don't. What I do have a copy of, and if you printed out the note frames you also have a copy of, is a table concerning a certain normal distribution that's in the back of virtually every business analysis textbook there ever was. This is the area of a curve that is to the left of a number of interest, except, wait a minute, it's a very particular curve. It is the standard normal curve. Standard normal. You say standard normal curve, it's a particular curve. What curve is that? It is a normal distribution whose mean, the center, happens to be 0. Not 2.75, but 0 exactly. And its standard deviation happens to be 1. Pick a number, look it up here, the first 2 digits here, the third digit here. It's telling you the exact amount of the area of the curve that is to the left of the number that you just picked. You say, well, what use is that? Because our curve doesn't fit that description. Right, our curve doesn't fit that description, but you can take any normal curve and you can translate it into a standard normal curve. Super easy, and look up the area on the standard normal table. That's why it's the standard normal curve. Now, translate. How do I translate my particular curve that has the center of 2.75 and the standard deviation of 0.25? How do I translate it into this one particular curve with a center of 0 and a standard deviation of 1? That's what the z-score does. Z-score. Oh, that's why there actually is a z right here, not an x, the number that we're interested in, but a z. To translate the question into the same question for a standard normal curve, you just say x, the number you're actually interested in, minus your mean, your curve's particular center, divided by your curve's particular standard deviation. That translates your x, the number that you are interested in our case 6.75 days, to the equivalent spot on the standard normal curve, and perfect, we can then use the table. Oh, right, that's why, go back to our original workspace. That's why there's a column here for z-score. Because for path AEI, z-score 6.75 was the number that we were interested in, minus 2.75 is our particular curve's mean or center, divided by our particular curve's standard deviation, which is 0.25. All right, I did all this on my calculator, and I get a z-score right here of 16. So for path AEI, the z-score I get is 16. You say, oh, all right, so that's the equivalent spot on the standard normal curve. Let's go look up 16, because you see this, the probability of completion within 6.75 days. The first two digits are here. The third digit across the top is the column, and I don't see 16 anywhere. Basically, this table quits around 3. Our z-score is 16. It's literally not on here anywhere. Oh, you know what that means? It means, remember the original question was, we were a little worried, AEI, that sequence of tasks, what's the chance that we would be done within 6.75 days? The answer is, don't worry about it. You'll be done within 6.75 days. If a z-score, the general rule of thumb, if a z-score, once you've computed it for a path, comes out greater than 3, just treat it as 100%. That's not a path that you're worried about when you're calculating risk. Oh, all right. So numerically, that's a probability of 1 for, 100%. No problem. Basically, AEI is so short, it's not going to create a problem with respect to 6.75 days. As opposed to, now wait a minute, I said that, count them. There are actually 3 paths through that original network. As opposed to, how about A, C, F, G, H, I? And that should sound familiar. What I just rattled off, A, C, F, G, H, I, that's the original critical path. That's the original critical path through this network. Oh, which means that is the path that is exactly 6.75 days, right? Path mean, right here, because that's the reason the project is 6.75 days. Okay, now wait a minute. What is the path standard deviation? We have to do more scratch work. So I'm going to draw a little border here, just to keep my notes organized on each of these 3 paths, because what I need to do here is to tally up the original variances of each one of these tasks. Now remember how the variance in A was 0.0069? We already used it up here. It's also here. The variance in C was 0.3403. When we originally tallied it, the variance in F was 0.0278. The variance in G was 0.0069. The variance in H was 0.0278, and the variance in I, which is also right there, was 0.0278. I add those up to get 0.4375. That is the variance in the critical path. You find the variance in a path by adding the variances along the path. Oh, now for the z-score, what we want, and what this column is labeled as the standard deviation, now that we've done the adding, we take the square root. Okay, so that's a standard deviation. Take the square root of that right there, and I get about 0.66. Okay, good. That's the number that we need for over here, because over here we go 6.75 is the number we're interested in. 6.75 happens to be the mean of our path divided by the 0.66 that I worked so hard to find. Wait a minute, 6.75 minus 6.75, this is a z-score of 0. Right? The numerator is 0. This is a z-score of 0. Z-score of 0, take it over here. Oh, well, actually 0 is on the z-table because 0.00 is right here. It says 0.5. Oh, right. That happens to be the exact center of the curve, the 6.75. So we asked the question right where it's cut in half. That makes sense. Half of it's to the left. Note that. Probability of completion within 6.75 days, that one path, 50%, or 0.5. And then finally, we have to do this for each and every path. There was one other path. You can find one other path through that network. Let me draw another little border here, just to stay organized. Because the other path through that network is BDGHI. It's just a route from start to finish. If you add up the task lengths along it, you get 6.25. If you add up each one of the variances, get the grand variance, take the square root of that, right? What we did here and what we did here, check me on this. You get 0.45. That's what you use in the z-score because you say 6.75 minus 6.25 is this path's mean divided by that 0.45 that I just quoted you. I get a z-score of 1.11, the z-score. Okay, 1.11. 1.11, what does that tell me? I take that to the z-table, 1.11. The first two digits are the row. The third digit, 0.01, completes it, the column. You're looking for the intersection. It says 0.8665. 0.8665. 0.8665. Basically there's about an 86-87% chance that you'll get done with that sequence of tasks in 6.75 days. Oh, all right, now what have we done? We have found the probability of getting each one of those paths done in 6.75 days. Have we answered the question? Because the question is, well, what's the probability you'll get the project done in 6.75 days? We remember the project's not done until all the paths are done. So one method per analysis for estimating the probability of getting the whole project done in 6.75 days is to calculate the joint probability of successfully completing all its paths. How do you calculate joint probability? You have different individual probabilities. Multiply them times each other. So, to answer the question, finally, I'm going to squeeze it in down here at the footer. Answer. The question is, within 6.75 days, I say 1, right? The 100% probability times 0.5, the 50% probability, times 0.8665, that probability, each one of the paths, I get, whoa, wait a minute, 0.4333, or basically about 43%. The question was, what's the probability of getting done within 6.75 days? We are quoting that as the expected completion time of the project, the 6.75 days. But oh, by the way, according to this analysis, that if you told the client that, there's only about a 43% chance that you'd actually get done within that amount of time. Oh, and that doesn't sound really good at all. Now, also in this scenario, a second question is posed because we were told something important at the beginning. Missing the 7-day deadline would be disastrous to the client. Okay, we found out 6.75 is not too terribly different from 7. We found out there's only a 43% chance of getting done within 6.75 days. Now we turn our attention to the disastrous if we miss the 7-day deadline, and we ask the question again. Furthermore, what is the risk that Epic will, oops, and we need to be careful here. Notice this question is phrased slightly differently. Not finish in time to meet the 7-day deadline. Last time we worked on this, 6.75 was our X, the number of interest. Now the question, the second question, it's 7. Okay, so we're giving ourselves a little bit more time, but we're also asking a slightly different question. Not the probability of getting done within the deadline, but the probability of not getting done within the deadline or disaster, according to the first paragraph. Oh, well, what do? Well, the first part is just a repeat of the analysis that we just did. We go through those steps again because we have to calculate first the probability of getting each one of the paths done in 7 days. Oh, all right. So for instance, there's AEI, right? That's the same old path and the same old mean, 2.75, and the same old, because now we've found it, we don't have to find it again, standard deviation, 0.25. Z-score. Z-score should be slightly different because we say 7 minus 7 minus 2, not 6, 2.75, right? The path mean divided by 0.25, the path standard deviation, I get 17 as a z-score. 17. Oh, wait a minute, last time it was 16, now it's 17. Remember our rule of thumb, if it's greater than 3, forget about it. Oh, yeah, you know, we weren't worried about path AEI back when we only had 6 3/4 days. We said 100% or a probability of 1. Now we have 7 days to get it done. We're still not worried about it. That makes sense. Okay, but we better check the other paths. The critical path, A, C, F, G, H, I. All right, same data as last time. The path mean is 6.75. The path standard deviation 0.66. We don't have to find that again. The z-score, 7 minus 6.75 divided by 0.66. I get that is 0.38. There's our z-score for this particular path. Okay. I'm going to need to look that up because what's the probability of being done within 7 days? I look up my z-score. The first 2 digits would be here, 0.3. The third digit, I need to find 8, 0.3. Stay on the correct row, 8, 0.38. I see 0.648. 0.648. Okay, from the table. And what's that mean? It means there's about a 64-65% chance of getting done with that sequence within 7 days. Now, we're not done until we've done all the paths. The other one was B, D, G, H, I, same as last time. Same path mean, 6.25 days. Same path standard deviation, 0.45. Don't have to find that again. Do have to calculate another z-score. Now I've got to scoot down here and do that. Because I say 7 is the number I'm interested in, minus 6.25 divided by 0.45. And I did that, and I got 1.67. 1.67. I better look that up. It's less than 3, meaning I can't just count it as 100%. 1.67, 1.6, and 7. There we go, right there. 1.6, and the column is 7. It says 0.9525. 0.9525, 0.9525. Oh, there's about a 95% chance of getting done with that particular path in 7 days. All right, now I have the individual path probabilities. I next find the joint probability of getting done with the project within 7 days. So I say joint probability. Okay, 100% times 0.648, that's coming from ACFGHI, times this 0.9525 from BDGHI, 9525, I left out a 5, 9525, that number right there is what I meant to write. Okay, I did that, and I got 0.6172, right? This times this times this, 0.6172. So, you say, okay, great. At least it was a little faster this time. We answered the second question, right? No, actually we haven't. We have to be careful. We almost answered it. But if somebody asked us that question that's at the top of the page, and we replied 0.6172, which I just wrote and put in a box, we would be wrong. Like we would miss that question. Because the question asked at the top of the page, what is the risk they will not be finished, or they will not meet the 7-day deadline? This that I drew a box around is not incorrect, but it is the probability of within 7 days. They have about a 61-62% chance of getting done within 7 days. So what is the chance of disaster? One, last calculation, 1 minus 0.71 or 6172, 1 minus that number, I get 0.3828, or about 38% chance of not, that's what they asked, not finishing in 7 days. So that's the answer right there. The conclusion is, if it would truly be disastrous for the client if this project is not done in 7 days, well, if you go the way you're going right now, there's about a 38% chance of disaster.